Okay, students, let's begin lecture. Welcome back from the weekend. Uh, Boy, that was a game on Sunday. 1 point, one basket. And they could have almost knocked off Duke. Duke was breathing hard. They barely made it. We'll get them next time. All right, we're going to talk about equilibrium temperature, how to calculate it. Move on down from the back. Are you in my class? Okay, move on down. Move on down to the front. Equilibrium temperature, we had a little intro to it in homework 12. We're going to go through that together, and we're actually going to calculate an equilibrium temperature in just a minute. But before we do that, let me just remind you that we have SI today, 2:30, and then tomorrow at 3 o'clock. And I know that it's helping out a lot of students, and so that's really good. Now, the main, and by the way, office hours on Wednesday from 11 to noon in the Physical Sciences building. Equilibrium temperature is our main topic for today. It's kind of an important thing to know about if you're working in a lot of areas. Now, here's something you may have seen. A blacksmith, and this is kind of old-timey, but there are blacksmiths that still do fine work, and they're they're highly skilled. What they do is they heat up the steel to a high temperature so that it's malleable. They could form it into the shape that they want. And in a big foundry or a forge, they do the same thing, but they heat it up, and then maybe they pour it into a mold, or they put it into a forge and kind of pound it into shape. But they do that with a certain temperature. And then what they do after that is they quench it in, for instance, cold water. Like here's a blacksmith dipping a piece of red hot steel into a pail of cold water, and here's another picture. Here's another guy dipping a piece of steel into cold water. And the precise temperatures that you have when you start and when you finish are really important as to how hard the steel becomes. They do this quenching in order to harden it. And then they do another process called tempering, in order to first make it hard, and then tempering makes it a little bit softer. They notch it back down again, because something that's hard is also brittle, and it can't take a lot of pounding. Now, tools have to take a lot of pounding. Other things don't. So what they do is tempering, and that's with slightly less cold temperatures and stuff. But all that's really, really important, and not just for the old-time blacksmith, at the OK Corral, but, any kind of metalworking. And that's just metalworking, metallurgy. There's all kinds of reasons that we care about equilibrium temperature. So let's review exercise 8, which I set up for you over the weekend. And I know that there were some students asking about, well, how do you get that number 8? So let's take a look at it. Both substances were above the melting or freezing point. They were both liquids. Substance H and substance R, and but they weren't in equilibrium. Here's the specs. The initial temperature, that's the fourth column here. Substance R started out at 1,000, and these are imaginary substances. I just made them up, and let the numbers do the talking. So substance R is 1,000 Kelvin, and substance H a little hotter, 1,100. All right. So they've got a gap in the temperatures of 100 Kelvin, so they're not in equilibrium. So what that means is that substance R warms up, and then substance H will cool down. And they do it by exchanging energies. All right? So the energy that goes from substance H, the hotter one, will warm up substance R, the cooler one. So calorie for calorie, you know, it just warm, and really it's on a molecular basis. If we believe in the kinetic theory, then it's really molecule for molecule from substance H and substance R interacting thermally. So thermal equilibrium is eventually reached by exchanging a certain amount of Q, a certain amount of thermal energy. And that's where the equation came in that I heard somebody talking about when I came walking in the back door. Q equals MC delta T. That is what you need for homework 12, problem 8. Okay, and I said that R gains 100 calories from substance H, and substance H, of course, that means the substance H has lost those 100 calories because it's insulated in styrofoam, so there's no net heat loss. There's just heat exchange. And I was looking at these temperatures, and I thought to myself, yeah, that's pretty tough styrofoam. It must be the new fireproof styrofoam that won't melt. If you've ever been on a camp out with a campfire, you know that throwing styrofoam into the fire is kind of dangerous because it melts and it's really bad if it burns. You know, if you get hit by a little flying droplet of styrofoam, it can really give you a bad burn. Anyway, so eventually these guys will reach us, or will reach thermal equilibrium, and that's what the thermometer will be able to measure. When that thermometer stops going up, it's dipped into substance R. So as soon as it stops going down, it's dipped into substance H. So as soon as substance H cools off to whatever the equilibrium temperature is, the thermometer will stop at that temperature. Now, homework 12, problem 8, was really about this item, 3A. You know, R gains 100 calories. All right. Ooh, let me pause for a second here. I forgot. All right. So, homework 12 is about 3A. Homework 12, number 8, and number 7 is actually about item 2 here. You know which one. You know what each one of them does. All right. So let's take a look at this. Here's our original table. Let's get it out of the way, and let's just use the part that we need. All right. So we have 100 grams of substance R, specific heat 0.336 calories per gram Kelvin, melting point 807. We don't really need that. We're going to use 1,000 initial temperature, but really all that we need to figure out the question at hand is Q equals MC delta T. Now what we're going to do is plug in what we know. All right, and we know that Q is 100 calories. We're saying that what happens to substance R when it gains 100 calories. Well, 100 grams of it at 0.336 calories per gram Kelvin is going to gain a certain amount of temperature, delta T subscript R. So this is the thing that we want to figure out over here. All right, delta T subscript R. So in the heat melt heat, we were trying to figure out, we knew what delta T was, and we tried to figure out Q. You know, how much energy do we need to heat up a certain amount of ice, etc. This time, for thermal equilibrium, we have the initial and the final temperatures, and we're trying to figure out where they come to a equilibrium in between, but we don't know where that is. So that's how we figure it out. We figure out these little increments of temperature. All right, so here's your thing, and if you notice here, you can, and hey, you guys, you should be jotting this down because you're going to be doing some clicker questions and calculations here in just a minute. Okay. And that's why I'm going through this in detail. And your homework tonight is to do the same thing. I'll give you some homework problems on thermal equilibrium. Anyway, so you've got this set up. So this is your plug-in step. And if you look at it carefully, you can calculate, or excuse me, you can cancel grams on the right side, right there. The grams in the mass and the grams in the denominator of the specific heat. Okay, so that's good. So now if you multiply 100 by 0.336, you get 33.6, and it's now calories per Kelvin. And that's times delta T subscript R, and that still equals 100 calories. Right now what you do is you divide both sides by 33.6 calories per Kelvin, and that'll get delta T subscript R by itself. This is just algebra time now. Okay, so here's your last algebra step. And here again, you can see that there's some cancellation. Actually, you could have canceled on the previous step, the third equation block. But I'll do it here. Calories cancel from the numerator and also from the numerator of the denominator. Now, the denominator of the denominator, it's division by a fraction, so it flip-flops it. And so really what you have there is Kelvin, 100 divided by 3.36, 33.6, and that works out to about 2.98 Kelvin. Now double check me on this. You're going to all need your calculator. So double check me. 100 divided by 33.6. You got it? Okay. All right. Now on the problem, I asked you for the temperature to the nearest tenth of a Kelvin. All right, and we're going to work to tenths of a Kelvin today in clicker questions. All right, so make sure you have your clicker. And in the homework it was 3.0. That would be the correct answer. All right. So what we're going to do now is clicker time, and what we're going to do, here you go, is calculate delta T subscript H. Same process, but substance H is losing 100 calories. So everything that we did in this problem here with Q equals MC delta T, we had 100 calories positive, and then we calculated delta T subscript R. You know, we got all the algebra, cancellation, all this jazz, and divided by 33.6, and we got an answer with some more cancellation, 2.98 Kelvin, or to the nearest 10th, 3.0. So that's what we're going to do again. So actually, let me pause here, make sure I'm not losing anybody out of the circulation. If you have a question, ask me right now about this calculation. Okay, let's do it. Clicker time for delta T subscript H. Now it's going to be negative because Q is negative 100. All right, so here we go. Calculate delta T subscript H when it loses 100 calories. All right, and here are the specs that you need. Here's your table. And H is now we're using the stuff from the bottom row for substance H. And type it into the nearest tenth, and it's going to be a negative, so you're going to have to find that negative sign in your symbols. And let me start the question. And but go ahead and start working on it, and definitely, collaborate with your neighbor and make sure you're double checking each other. You know, I wish this was a smaller classroom because everybody's so spread out. There's so many of you that are just sitting by yourselves. You're not sitting with anybody, and you can't consult with your neighbors and stuff, which is beneficial. Okay, go ahead and start. So this is the cool down amount. You know, substance H loses 100 calories, and really there's nothing special about losing 100 calories. Make sure it's a negative. Don't give me a positive. All right. Go back and change that to a negative. Everybody should have a negative number here. Because Q is negative. You're losing. You're cooling off. Delta T is negatory. That means you're going to a cooler temperature. All right. Now, they're different substances, so you're not going to get 3.0 or negative 3.0. You're going to get something different. But that's all right. You have a different mass, and you have a different specific heat. So what do you want? So type in your negative number, something, point something, and then, no, negative something, point something, and then hit the send key. Okay, you guys are doing good. Uh-oh. I see a little round. Make sure you round off carefully. And use your decimal points. Okay, good. You know, H is a smaller mass, so it'll be slightly easier to heat up on that basis because there's not as many grams. But it also has a bigger specific heat. So my guess is looking at those two numbers, 100 grams versus 86, 0.336 versus 0.828, my guess is that H is going to have a smaller delta T, or the absolute value of it. It's going to be probably going to get something smaller than 3. Negative something smaller than 3. All right? And just keep calculating away here. You're doing good. Now this is our entire objective for today. So we might dismiss a little bit early so you can get to that homework. All right. And I'll get the homework up for you by supper time or so. It'll be fairly simple, fairly small. Don't blab the answers out.
You heard me?
All the way over here. Gosh. Did you hear him too? You hear him? Yeah. I'm halfway across the room. So you couldn't hear him all the way. But some people you can hear all the way in the back of the room from the front. Yeah, it's all right. Okay, 1 minute to go. Starting now. And this is the same kind of calculation. You guys look like you're doing pretty good here, I would say. "30 seconds. "20 seconds. "10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Make sure you've hit the send key because it doesn't have your answer unless you hit the send key. All right. Let's double check the solution. You guys did pretty good, I can tell. So here's your plug-in. Okay. Negative 100 calories over on the left. That's your cue. If something's cooling down, it's losing energy. All right. And the mass in this example, and you have different examples in web courses or different instances, so you might have different, slightly different numbers. Anyways, 86 grams and 0.28 calories per gram Kelvin, and that'll allow you to figure out delta T. So then, okay, the first two numbers, 86 and 0.828, multiply out to 71.208 calories per Kelvin. Cancel calories both sides and divide by both sides. Negative 100 divided by 71.208, that's going to give you kelvins. So negative 1.4 Kelvin. Raise your hand if you got negative 1.4. Very good. Okay, good. Now, if you didn't get it, make sure you jot this down or go back in the YouTube and review it. This afternoon after I post it to YouTube. Question?
The symbol Q, that's thermal energy?
Yeah, Q is the customary symbol for any kind of heat energy. And I think if you raise your hand if you've had a chemistry class here at UCF. Whoa, not too many of you. In chemistry class, they have something called the heat of enthalpy. When they're making reactions, some reactions produce heat, some reactions require heat, and they usually use the symbol Q for those. And then enthalpy is the symbol H and stuff, I think. Anyway. But Q for us is thermal energy. All right, so go ahead and make some notes here. Here's the upshot of our first two calculations, one from homework and one from class here with the clickers. H cools down by negative 1.4 Kelvin. R warms up by 3.0 Kelvin. Every time you exchange 100 calories. So now here's the logical result of that. Substance H started at 1100, but now it's at 1098.6. Jot that down. Substance R in the droplet was 1000, and now it's a little bit warmer. So it's warming up a little bit more than substance H is cooling off. Deanne.
So Q isn't on the homework question. Was Q not calories?
Yeah, Q is measured in calories, and I gave you the Q value of 100. Okay. And we're doing, and now we just did the minus 100. So when we're doing the thermal equilibrium, I always talk about it in terms of plus or minus Q or plus or minus delta Q. All right? So now look, we started out with a gap of 100 Kelvin. Now, and this is important, now the temperature gap is 95.6. Okay, go ahead and jot that down. All right? And that is important. So they're still not in equilibrium. If you have a gap like that, they're still out of equilibrium. There's going to be more heat exchange. I'm going to ask you some clicker questions here in a second to really rattle your brain. All right? So there's going to be more heat exchange, and equilibrium will be reached when the gap is 0, and that's when the net energy exchange ceases. All right, so when we get that gap close to 0, or at exactly to 0, if we calculate it right, then that will be the equilibrium temperature. It could be anywhere, somewhere above 1003, somewhere below 1098.6, because we know that's the process has not finished. Now we're going to do some multiple choice. So hit the refresh key. All right, and let me just go backwards here and remind you. We had a dip of 1.4 and a warm up of 3 Kelvin. And that means the temperature gap is 95.6. And so, we're not at equilibrium, but we do want to close that gap to 0. So here we go. Hit the refresh key. And approximately how many additional times will substances R and H exchange plus or minus 100 calories before they get to equilibrium? In other words, how many times do you have to exchange 100 plus or minus 100 before the gap's down to 0? Right now, think about that. Talk with your neighbor. think it over, and I get, figure out how many exchanges. Because each exchange, the substance R dips by or warms up by 3, and substance H dips by 1.4. So you can. So think, my students, think. So, I mean, the next exchange of 100, substance H is going to go down by another negative 1.4, and substance R will go up another 3, and the gap will be smaller. And you keep doing that, and eventually the gap will be down to 0. And that'll be and then they'll both be at the same temperature. But let's see if you can use your mental logic here. Think of a solution. One minute. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let me stop this. Get this out of the way. You guys did pretty good, actually. Approximately 22 exchanges is what you need. And so a total of 23 to complete the process. So here's how you do it. You got a gap of 95.6. Now every time you exchange 100 calories, that means your gap closes by 4.4. One of them comes up 3, the other one dips 1.4. So there's a total closure of 4.4. Right now it takes about 21.73 dips, or exchanges, I should say, to get down to zip zap. That'll square away your 95.6. Now we already did one, so that means a total of 22.73 for the entire thing. Now, let me just show you why this is important. Figuring out the gap, figuring out each delta T, and knowing the initial temperatures and stuff will help you figure out all that. Because you can figure out in one step an exchange of 2273 plus or minus 2273 calories. That'll get you one calculation directly to the equilibrium temperature. So you can inch it down by 100 calories, and there's nothing special about 100 calories. You could have used 10 calories, and then you'd have a whole lot more exchanges. But then you could do this trick and figure out how many exchanges you need. Or you could have done 50 calories, and then you'd have fewer exchanges to calculate. Or you could have guessed, been a total luck shot and said, okay, I'm going to guess 2273. Let's see how that works. And you would have been right on it. But most of the time, you're not going to guess right on it. So you got to work through some process like this. All right, so let's get the equilibrium. Let's bring this all the way home. Let's get equilibrium temperature for this problem. And here's how I want to do it. You guys in the center section, I want you to calculate delta T subscript R. All right? And that's for gaining 2273. So there's your new Q. You guys over here in the side sections, so over here and over here, I want you to do delta T subscript H. So figure out the cool down delta T. And then for a Q of minus 2273 calories. And then for extra safety, double check your opposite. Do yours first, and then check, you guys on the sides, check the center. You guys in the center, check the sides to see if they're right. Okay? So go ahead and take that, and we're going to take minutes to do that. And let me hit the refresh key. I'll let you type in your answer. Hit refresh, and let's do this. And just work slowly and just, nice and easy, and, try to get it right. R is 100, H is 86 grams. And let me turn on the lights for you guys. So you can have some light. Ooh, nobody's answered yet. Good. Work nice and easy. Tenth of a Kelvin. So something point something. And some of you will be positive and some of you will be negative. But this should do it. I mean, you both should come up with the same delta T. So Q is either plus or minus 2273. And just for safety and for bragging rights, check your opposite. Link. You're frustrated? Feeling it? Come talk to me after lecture. Question? What's that? 10th of a Kelvin. So something point something, either positive or negative, whichever one you're doing. Yeah. Type in your number. I'm going to grade everything appropriately. I see some good answers, but some of you should be putting in negatives and you haven't. From what I can see. And there's some round off troubles. Give me your answer to the nearest tenth, whether it's a negative or a positive. I can grade everything on a numeric problem like this. Any answer that you'd send, I can grade it correct or incorrect. Make sure to hit the send key. I didn't hear your answer. Good.
We disagreed about it.
Good. Okay, 1 minute.
Yes.
20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 88 answers. All right, take your answer, your negative answer, you guys on the sides, because substance H is cooling down. Subtract that from 1100 and write down your thermal equilibrium temperature. You guys in the middle that did T subscript R, add that to 1,000, add your answer to 1,000, and that's going to be your thermal equilibrium temperature. All right, now you've typed in your delta T. Now you're figuring out your thermal equilibrium temperature. All right, so write that down. And I have a question for you. And I have a feeling I know that's going to be a lot of you. Is your thermal equilibrium temperature close to 1068? Raise your hand if you have 1068. Oh boy, you know, there should be a whole lot more of you. You're not doing something right. You have good answers, but you didn't do it. You got to take your, let me repeat it. Center section, add your delta T subscript R to 1,000. Side sections, take your delta T subscript R, it's a negative, so subtract that from 1100. And are you getting 1068 thereabouts? Okay, good. All right, now let me show you the answers here. Let me get this over here. Here are the answers, and actually, let's see if I can maybe this. All right, negative 31.9. That looks about right. That's the dip in temperature for substance H. And these guys down here had minus 32, negative 31.92. Here's somebody that forgot the minus sign. All right? So that'll get you from 1100 down to about 1068. All right? Now, here, 67.6, That rounds up to 68. So that gets you up to about, that's delta T subscript. That's delta T subscript. Let me get this back. That's delta T 67.6. That's delta T subscript R to the nearest tenth. So, yeah, so getting 1068 is pretty righteous. And most of you have the right numbers. These two students down here messed up. I don't know if I have any more. This thing is extremely hard to operate. 35.3. That's a miscalculation of some kind. Negative 31. That's too much round off. 0.04, 0.4. These ones are 31.4, 67. 516. 676. This one, you missed your decimal point. I don't know what this one is. Anyways, you guys did good. Now, let me dip out of there. We're going to dismiss. Homework 13 is going to include some thermal equilibrium brain burners. And, just work on it the way I showed you, and you should be able to do it chop, chop. And make sure you have plenty of attempts and plenty of time for the thermal equilibrium calculations. Okay, you're dismissed. I'll see you on Thursday. We're still ahead of schedule.